Okay. Hi everyone. Today we are gonna start to the autoencoders in machine learnings. Firstly, we need to define the R structure and the pattern in here. Suppose that we have neural network like this one. For example, the X1, X2 and X3, and this is the input neurons, and this is the hidden layers, just like this one. At the end of this code we output Y. Okay, this is the basic neural network structure, and so we can building in here X vector to what Y, like this one. We can generate the nonlinear f function with the input values of the X. Okay. But in this generation we can decide either the we can determine in this case the signal generation. This is the GAN structure, generative network, or we can classify or regress the data based on the for a given input and output relations. But we have also topics just like this one. Firstly, we need to write that the unknown representation of neurons and the hidden layers should be discussed in here. Unknown representation of neurons and hidden layers. Just remember that in the neural network, if we have any hidden layers and the neurons within in these layers, and so we can formulate or visualize in the geometry. But if we use the deep neural network, and so we cannot easily represent the unknown data because it's a deep. Okay. It's called the hidden. This is why we call it hidden. Okay. And also in this case we optimize, or the optimization is applied to build only to target or signal. We can map to the for a given X to the Y. Okay, this is a map in here. And also this NN structure is creating to the learns in a way of supervised. Okay, which means that we have the input and output data, and so we can match and map this data for a given the neural network. Okay, so in this case we cannot code of the input and output data. We cannot learn the input features, just mapping in this case. Okay, and we cannot learn anything about the main features of this data. So the main result of this code, the problem, I can write this in here in a complete case. Firstly, we cannot coding X and Y, just mapping is identified. We cannot build the X in here. We cannot know anything about the X and Y, just mapping of this data. In the second place, we cannot learn not the input features. We do not know anything about the input features in here. And also we cannot learn anything about the main features, because we built only the what to the map of this case. Okay, so in order to clarify the problems, we need to define this case in here, just like this one. The problem can be summarized or simplified just like this one. Assume that we have 3 signals. Like this one. These are the axis endpoints which is given in here. First of all, we have 12 and 5 and 2. Okay, and also we have the distribution of this kind of data in here, just like this one. Okay, in the signals we can write to the what signals with a mean and noise or variance value of this signal. Okay, and so the main part of this signal is related to what? First of all, the 12 or 5 or 2. The other parts are considered as to the what? As the noise. Okay, and so in this case we just have to the what? 2, 5 and 12 signals with the mean rate. Okay, and also these 2, 5 and 12 should be learned in here, because the other parts are the noisy one. Okay, and so the main problem is that how can we do that? Because this is maybe the X signal in here, this is the input signals, and so we need to learn about everything in the what? In the input signals, guys. Okay, not the output one. Just remember that if we have the noisy data, and so we need to remove or eliminate the whole noisy data coming from the what? The main components of this one. So the solution is given by with the what? With the following structure. Firstly, we need to understand the coding in terms of the what? In terms of the input and output in an structure can be given by just like this one. If we have any x vector in here, if we want to learn this x, and so we need to build the what? The neural network in here, just like this one, and so also we need to output or generate the same x values in here. Okay, so if we design and then taking to the what? To x and generate to x hat, and so the efficient coding is done in here. The efficient coding is done here. Okay. So what's the meaning of this? In this case, we feed the x data and generate the x hat data. This is the same with the what? With these formulations. And so if we put the x with the noisy values, and so we will get to the what? The mean values of the x hat, if we have trained the neural network correctly. Okay. So let's turn into signals like this one. For example, if I put the axis in here with the n and x values, okay, and so for example this the 2 is the signals in here, and so this the straight line in this case. Okay, and so the main parts is given in here, but maybe we have to the what, to the these signals, just like this one. This is around to 2.2, but this is the mean values and this is also the noisy parts. Okay. And so this signal is the complete signal, this signal is the mean of this signal, and this is the noisy parts, okay, or unwanted parts, okay, which we call it to the noise. And therefore we need to find out the main important representable part of this signal. Just like in the mechatronic engineering, we want always remove the what to the noise value, because everything is the expected values in the probability theory or the mechatronic or the mathematics, because the expected values is represented with the what, with the main components or the main features of this data. For example, is a sensor data, or for example the human body mass or the height, okay. But in real life we have this complete signals, okay. And so we need to find out the main important representative part in this case. So how can we do that? Firstly, we need to write this diagram. Normally the NN is created by with the what, with the input, hidden and output neurons, okay. But suppose that we have these three neurons structure in here. For example, x1 is input, x2 and x3, and also x1 hat, x2 hat and x3 hat want to generate it in here, okay. And so this is linked with the every neurons in here, just like this one, okay. And so in the setups we have at the each case the n is equal to the 3, or neuron number number 3, number 3, number 3, number is 3. And so if we minimize the error between output and input for this NN, then the minimization is done at the first step. We cannot learn the main parts or the noise parts, because the every stage neuron numbers are equals to each other, which means that we don't need to what? Not need to learn anything in here, okay. For example, x hat is equals to fx, and so f is simply is just like 1 and so it multiplies with the 1, and so the output x hat can be generated in here, okay. So in this setup, this is directly transit to the what, x vector to the x hat, without selecting the main parts, okay. So in the second setup we should write to the what, to the x1, x2 and x3 and now this is the n is equals to the 3 in here, but in the hidden layer we have too many neurons, okay. This is the bigger than n, okay. And also we want to generate the x1, x2 and x3 values, but the hat values is generated in here, okay. So In this case, if we minimize the error, then we imitate the both main part and the noisy part, because we have higher number of neurons than the input one. Okay? And so in this setup, we can learn both the main and noisy signals. Okay? And we can force to learn to represent the parts, but we can create the more additional abstract features. That's not meaningful. Okay? The main part or the mean part can be called the meaningful part, but noisy signal is not. Okay? In this case, if we increase the dimensionality of this neural network, and so we can build to the what abstract feature to represent the unwanted noise signals in here, which we don't need that. Okay? Because in real life, it doesn't mean anything. And so, in the third setups, we have, for example, x1 and x2 and x3, and also we generate what many input features in here. Okay, just like this one. But however, at this case, for example, this is the 8, this is the 3, and in the input layer this is the 8, and so we can choose to the what, to the smallest part, or the lowering neuron numbers at the what, at uprising the hidden neurons in here. And after that, we can generate the more or use the more neurons in here, just like this one. And after that, we can generate the what, to the x1 hat, and also x2 hat, and also x3 hat in here. And so this is the generation of the what, the R hidden layers. And then what? This is the 5, this is the 3, this is the 5, this is the 8, and this is the 3. Okay? 5, 3, 5, 8, 3. And so, in this setup, if we minimize the error, we push the system at the representation to be forced with a small number of neurons. Okay? Because in the dimensionality, this is the lowest part. Okay? This is the standard NN. And so after that, the generation of small output in the second part of this one. And so if we accomplished with the what, with the lowest error values in here, x minus x hat. Okay? And so if we minimize this error, and so this section should be creating to the what, the highly representative feature. Because the dimensionality is decreased, and after that it increased right now. Okay? And so we don't have any unwanted noise in here. Okay? And so in Turkish bakın arkadaşlar, standart olarak bizim bir nöral network'le ya sinyal üretiyoruzdur ya regresyon yapıyoruzdur ya da sınıflama yapıyoruzdur. Ama biz bunun girişlerini, çıkışlarını asla bilmiyoruz. Çünkü biz bunu supervise'le eğitiyoruz zaten. Gözetimle eğitiyoruz. Şimdi bakın, asıl problem şu. Eğer bize bir 12'lik ya da 5'lik ya da 2'lik bir sinyal verilmişse, bunların aslında ana komponenti ne oluyor biliyor musunuz? 12 ortalama değeri, 5 ortalama değeri, 2 ortalama değeri oluyor. Aslında bu. O yüzden bizim için anlamlı olan her şey aslında mean, expected value dediğimiz şey oluyor arkadaşlar. Ve bizim bunu öğrenmemiz lazım. Bakın, sonucu üretmemiz değil, bizim giriş verisinin ana komponentlerini öğrenmemiz lazım. Ne yapmak istiyor? Identify etmek istiyoruz. Onu tanımak istiyoruz. Onu öğrenmek istiyoruz. Bunun için de bir tane neural network ağ kuruyoruz. Buraya x veriyoruz ve x'i tekrardan üretmesini istiyoruz. Ama burada bir sorun var. Bizim bütün sinyalimiz ya ortalama ana aslında representative part'tan oluşuyor ya da noisy, gürültü part'ından oluşuyor. O yüzden bakın ben 3 tane neural network yapısı kuruyorum. Birincisi, bütün nöronları aynı katmanlarda aslında eşit sayıda nöron olan bir yapı kuruyorum. İlk yapıda aslında arkadaşlar x1, x2, x3'ü verdiğinizde aslında birebir buraya aktarıyor. Burada herhangi bir öğrenme olmuyor. Çünkü zaten nöronların eğitilmeye ihtiyacı olmuyor. İkinci partta eğer ki hidden layer'ın sayısını siz arttırırsanız zaten siz burada bu veriler x1, x2, x3'ün daha da üstünde yüksek aslında boyutlarda işlem yaptığınız için burada sanal olarak bu gürültüyü de öğrenmeye çalışıyorsun. Anlamlıymış gibi. O yüzden biz buradaki meaningful datayı bulamıyoruz. Ama bakın eğer ki biz 8 nörondan başlayıp 5 sonra 3. 3'ten sonra bakın 5 8'e çıkarsak ve yine x1, x2, x3'ü tanıtırsak aslında bakın şu kısımda 3'e kodlamış oluyoruz. Ama bakın burada 3 tane giriş verildiğinde bunun sayısını, hidden layer'ların sayısını arttırıp tekrardan çıkış alabilsek demek ki bunun aslında bizim ana komponentler, bizi var eden, bizi tanımlayan komponentler olduğunu söylüyoruz. Genel özeti aslında bu. Şimdi bakın literatürde in English for the third setup it utilizes to learn what unknown feature of data, not classification, not signal generation, not regression, unknown feature of data, identifying the data. Okay, and so then we can build to the what in the general form. We can build x1, x2 and xn minus 1 and xn and so this input layers is given in here. After that we add the what, the hidden layers in here just like this one, and also we build to the what at this case this one, and after that we increase the number of the hidden layers in here, and after that we want to output to the what, x1 hat, x2 hat, x3 hat, and also xn hat. In the literature this part is the what is encoding or encoder, and this part is decoder. Okay. And this part is the latent space. The encoder, this is the encoding input to the lower dimension. It is just like the zip, okay, the computer program, and so we can zip this data into this ones, okay, and after that decoder is utilized for the what, the decoding this zip file or the encoded data into input because we want to generate or obtain to the what, to the same values of the x1, x2 and blah blah blah. Okay, but what is this? This latent space is the main characteristics of these data distributions x1, x2, x3 blah blah blah. Okay, and so this is the representative part of our model. Okay. In order to understand the advantage of this feature, and so you can check the article. This is the IEEE Access publication. Okay, I generated the physiological conscious autoencoder structure, guys. Okay, in the mechatronics you can use that way just like in my publications, but in this case we have to the what, to the encoding part and the decoding part. But in order to decode the encoded data, And so we need to generate the latent space, or in Turkish saklı aslında alan. Yani onun özelliklerini anlatan alan. And so if we create the training algorithms based on these ones, and so we can encode the lower dimension, and so this lower dimension are meaningful or representative, and then this can be decoded into the what? Into the generation of the what? The input data. Okay? And so this is the main structure of the autoencoder building. And so now we need to understand the mathematical formulation of it. Okay? Yani Türkçesi, eğer siz daha düşük bir uzaya bunu formülize edebiliyorsanız, şurası saklı özellikleri aslında verilerle alakalı bize verebiliyor. Ve bu saklı özelliklerden biz bunu oluşturabiliyoruz. Mesela benim yayınımda çok basit söyleyeyim. X'tat eşittir ax artı bu gibi bir değer var diyelim mesela. Bu sistemin aslında saklı değişkenleri a ve b arkadaşlar. Bu dinamiği oluşturuyor aslında. O yüzden ben latent space'te aslında gidip bunları yarattım. Sadece giriş ve çıkışı eşlemeye çalışarak. Okay. So, mathematical intuition behind autoencoders. In the bottleneck structure, what's the bottleneck? Bottleneck is the behind structure, main general structure. Okay, and then is forced to reduce information like noise, because this is the unwanted, and but only approximating original data. Okay, and so we can write to the what for the, we have three conditions: encoder, latent space, and decoder. Okay. So for the encoder we have just like this formulation, fx theta e. Okay, this is called the encoder in the mathematical formations. And so this theta e is the what? The latent variable, saklı değişken. And so the x is the what? Input. Okay, and so the f is built with the what? With the neural network coefficients, like the hidden neurons or the sigmoid function or something like that. Okay, and this is encoder. And what about this one? We can use this theta e values into the what? Into generate the x. And so this is the decoder. Okay, and so this data is the estimation of x. Okay, and so this g is the what? Is the decoder functions. So we can write to the what? These general solutions, the latent variable is the what? Is a hidden feature of data representation which cannot be observed directly. For example, for a human, we are made up with an atoms, right? But we cannot see the atoms. Atoms like the latent variable. Okay. So in these formulations we can write the total autoencoder formulation. The total autoencoder can be given by this one. We have the L, X, and G F X, okay, or L X X hat, as the L here the energy function, okay, to be minimized by using the neural network training, okay. And so this representing to the what the rate of how much closer to the real data at the output one, okay. And so we need to minimize this data when training, okay. And after that we can say that the X is the what X hat, but with a difference of what the theta e must also have obtained from these representations in here, okay. Şimdi bakın arkadaşlar. Bizim bir enkoderimiz varsa f fonksiyonuyla yapıyoruz. Teta'yı oluşuyoruz. Latent veriyor. Bunlar saklı değişkenler. Mesela insanlar atomlardan oluşuyor ya. Bu atomlardan oluşan insanlar arasında biz atomları görüyoruz ama insanı biliyoruz değil mi? Eğer ki biz kendimizi eğitseydik mesela böyle bir ağda atomları bulacaktık arkadaşlar. Bunu öğrenmenin bir yolu var. Dekoder de aslında G bir fonksiyon ama bu G fonksiyonu nasıl fonksiyon? Birden fazla katmandan oluşan bir sinir ağ modelinin aslında sonucu. Şimdi bakın buradaki autoencoder'in otokodlayıcının aslında temel formülasyonu ne? Bir tane enerji fonksiyonuyla gösteriliyor. Biz buraya bir x veriyoruz. Bu gerçek data. Ama bir de fx'ten ürettiğimiz bir de cx ile ürettiğimiz bir değer var. Yani aslında autoencoder'i aslında bütün verileri soktuktan sonra elde ettiğimiz yapı var. Bu yapıyı ben oluşturduğumda eğer ki L'yi sıfıra götürebilirsem training'den sonra, eğitimden sonra ben x ile x seti tekrardan oluşturmuş oluyorum. Ama bir tane farkla benim burada bir de saklı değişkenlerim de aslında oluşmuş oluyor arkadaşlar. Ve bunlar benim ana parçalarım. Ortak parçaların hepsini burada bulmuş oluyorum. Okay. So, the autoencoder structure can be written as just like this one. For example, the Z1 is the neuron output in here, H1, W1 times input X plus B1 here, okay? And so this H is a sigmoid function or the activation function, W is a neural network coefficient, and so B is a BS, okay? And after that, it can, and so in the second layer, we generate to the what? H2, and so W2 in here, this the input of this value is right now the Z1 and plus B2, okay, and so blah blah blah blah, and then and at the end of this code we have theta e, this the latent space variables hn, for example, times here, and so hn function of wn times zn minus 1 plus bn, okay. This is the what encoder part. Z is the output of the activation function, W nn coefficient, H activation function, and B is the bias value, okay. Arkadaşlar, istediğiniz kadar katman koyun, bu yapı değişmiyor. In the second place, the decoder is given by z n plus 1 equals to what? H n plus 1 times W n plus 1 times theta e plus B n plus 1, okay? And also blah blah blah blah. At the end of this code, x hat is equals to what? H 2n. W 2n times z 2n minus plus B 2n. This is the symmetric, okay? And so this is the decoder part. This is the encoder part. This is the decoder part, okay? Main building can be generated based on these informations, and so the total output is calculated as using the decoder 1 with the input values of the latent space. In order to provide the more efficient training, we need to concern about the another properties of the autoencoder in here, the regularization and the callback Liebler divergence formula, because in the next lesson, in the next week, we will talk about the variational autoencoder, guys. And so in order to explain the regularization, is a simple concept in here, L2 regularization. We can write or rearrange cost function L like this one. L hat is equals to L comma in here L plus lambda times Wi square I. Okay, this is the new loss and lambda regularization parameters param, and L is what loss and W is the NN coefficients. If we have this criteria just like this one, and so we prevent to the what the large weight or training causing to the overfitting in the modeling, because we don't want to overfitting neural network coefficients, because the overfitting can learn the noisy data, but we do not want to do that. Okay, because the model should represent the generalization capability of the test data. Okay, and so lambda is large and the NM weight cannot learn, but it is too small, the NN weight over fit. Okay, we should optimize the R data from the complexity and the generalization. This is the what optimization. We should select the correct number or values of this data. Okay. So what about the second param, callback Liebler divergence? This is important theorem, guys. Okay, everything is based upon this divergence theorem because it's a probabilistic rate of the measurement distribution divergence. Okay, and so it is a measure of how one probability distribution diverges from a second expected one. In Turkish. Arkadaşlar, bu Kiel divergence aslında size neyi söylüyor biliyor musunuz? Bir tane olasılık dağılımının diğerinden ne kadar farklı olduğunun ölçüsünü veriyor. O yüzden siz yeni bir veri üretecekseniz bunu kullanıyorsunuz. Eğer ki siz bunu minimize ederseniz hep aynı veriyi üretirsiniz. Eğer maksimize ederseniz çok farklı veriler üretirsiniz. Ama olasılıksal dağılımın içerisinde bunu yapabilirsiniz. Okay? And so, suppose we have P and Q distribution, probability distribution, okay, over same probability space. Just remember the previous lesson. X, okay, and so this divergence can be defined P Q is equals to what? The total summation of the Px times log Px Qx. Okay, this is the formula. And so how can we represent or interpret this data. If the P is equals Q in here in the first place, and so no difference, right? And so this is the 1, and which means that this is the 0. And in the second place, if DKL PQ is greater than 0, and so P and Q become distinct. This beautiful feature, okay? And so how can we utilize this feature in the autoencoder structure? Okay, the general sparsity rate or the formulation can be given by with the what? I is equals to 1 to the D key L rho I hat in here, and so I is equals to 1 D and rho log rho I hat plus 1 minus rho log 1 P no rho 1 minus rho I hat. Okay. And so what's the meaning of this equation? In this case, it takes 0 when the what rho is rho hat, right? This useful feature, average activation value, can be set using these terms in here. Can be set, and so we can condition our neural network to generate to the what diverge or converge data set at the what activation neuron structure or the output one. Okay, in the generative adversarial networks we utilize mainly these components in a different way with a different name. Okay. So any question? Okay, there's no questions, and so we need to take a break, and so we will start at the 7 p.m. guys. Okay.